Alright, welcome. In this video, we're going to be graphing secant x, cosecant x, and cotangent x. And to start, we're going to think about the graphs of cosine and sine. And we've graphed these a bunch of times. I don't think you need to see me go through the details of this. I'm just going to remind you, that cosine, okay, or maybe I'll start with sine, is going to be the one that starts in the middle and goes up, whereas cosine is the one that starts at the top and goes down. Okay, and we could put, because these functions are periodic, they repeat themselves, we could put the y-axis kind of in the middle, where I've got that vertical line, or we could put it at the far left side, or we could probably even put it at the far right side, because these are the graphs of two periods of each of these trig functions. I'm going to just put the y-axis there in the middle, and the x-axis is going to run through the center because these are just the standard cosine and sine graphs that have a midline of y equals 0. Okay, so I could put an x-axis in right there, and I think with these we're ready to start thinking about the graphs of secant and cosecant. Alright, so I might ask you, what do you think would happen to the graph of y equals secant x at x values where cosine x equals 0? Okay, so we know that secant and cosine are reciprocals of each other. That's kind of the whole lesson of the title of the lesson. We know that secant x is 1 over cosine x. They're reciprocals. So if cosine x was going to equal 0, secant would be looking like 1 over 0, and that's bad news. Okay, if cosine x equals 0, then secant x is not going to exist, right, because of the division by 0. And we know what happens to a graph when we have division by 0. We've seen it multiple times in this class in different scenarios. We divide by 0, or come close to that, we're going to have a vertical asymptote on our graph. Okay? So basically what I'm saying here is where we see zeros on the graph of cosine, these will be vertical asymptotes on the graph of secant. And same for sine and cosecant. Okay, so now if we want to sketch the graphs of y equals secant x and y equals cosecant x, I'm going to bring in the graphs of y equals cosine x and sine x to use as a guide. So each of these spots that I've highlighted in yellow correspond to the zeros of cosine and sine. So these are going to be vertical asymptotes. I'm just going to build these graphs of secant and cosecant side by side. So I'm going to come through here and I'm just going to draw, okay, I've got a vertical asymptote here and there, and another one here, and a fourth one right here. Right, because you probably don't need to watch me draw vertical asymptotes, I'll just copy in the ones for cosecant, which correspond to the zeros of sine. Okay, now, next, probably the next thing I would do is take away, I'll just work on the graph of cosine right now. I'm just going to take away the graph, most of the graph, I guess. I'll leave certain key points. Okay, I lost part of my vertical asymptote, but this is going to be all right. I'm going to leave certain key points, and I'm going to remind you that 1 over 1 is equal to 1. And that's relevant because at the top of the box that we've drawn, the top of the window, this is where cosine and sine are equal to 1. So that means that secant and cosecant are also going to equal 1. So these are also points on the graph of y equals secant x. And let's color them in a little stronger. Okay, and I got a little ahead of myself, but because 1 over negative 1 is equal to negative 1 again, well, I'm going to see the same thing down at the bottom. Okay, so these are points that are on the graphs of on the graph of secant x. Okay, the next thing I would say is that places where the function was, where cosine x was positive, secant x will also be positive because 1 over a positive number is positive. Okay, if you'll forgive my, abuse of the equal symbol there. So what I'm saying is that this secant function is positive the whole time while approaching a vertical asymptote. So it's going to look like that. And this one's going to have a little bit of this. Okay, that'll be all right. And some of that. And they kind of look like parabolas, but they are not. They're just kind of their own shape. It wasn't my best effort at it. They're a little more like U's. And if you go and use a graphing calculator, go on the internet, or see some of the problems on the homework that are professionally produced graphs, then you'll see the kind of the shape of these things. And the same story over here, intervals on which cosine is negative, secant will also be negative because 1 over a negative number is going to be a negative number. And the closer I get to dividing by 0, the larger my result is. 1 over a really small number, that's a really big number. It's another principle we've learned about in this class. So 1 over a negative number is negative, and there I've got myself the graph of secant x. And I'm going to bring in a y-axis and an x-axis, and there you go. Okay, so I think, much like cosecant, you will remember that secant x is the one that has the u's, and I like to remember that secant is the one that's centered around the y-axis. The y-axis is not a vertical asymptote to the graph of y equals secant x. But I'll come in and give you some more detail a little bit later. Okay, for cosecant, I'm going to do the same thing, clear out most of the graph of sine. You don't really need these middle points as much. Kind of do care about the extremes. Okay, yeah, that'll be fine. And the extremes are shared points on the graph of y equals sine x and y equals cosecant x. Okay, and places where sine x is positive, cosecant x will be positive. Places where sine x is negative, cosecant x will be negative. And we'll have a very similar looking graph. But that wouldn't be surprising to me because I know that the graphs of y equals sine x and y equals cosine x are also very similar. All right, so that's going to be the graph of y equals cosecant x. We're going to come through here with an x-axis. That wasn't really the best, but it'll do. And then the y-axis in the middle, just like it was before on the diagram of sine. And there we go. We'll have ourselves a sketch of the graph of cosecant x. Okay, I think the most distinguishing features of this graph is they've got the u's, okay, like secant and cosecant do, and the y-axis is a vertical asymptote. So I thought it might be good to, think about domain and range of these kind of originals before we start to transform them and ask you questions about those. Okay, so what I would point out is that, each of these windows, and I drew 2 windows originally of cosine and sine, each of these windows has a width of 1 period, which for the standard sine and cosine is 2 pi. So this is going to be x equals 2 pi. This would be x equals negative 2 pi. Which means that the vertical asymptote locations are going to be at pi over 2 and 3 pi over 2, and negative pi over 2 and negative 3 pi over 2. Okay, so they're repeating every pi. They're separated by pi, right? The distance between negative pi over 2 and positive pi over 2, or the distance from positive pi over 2 to 3 pi over 2, that's going to be a width of pi. Okay, so I'm going to say that the domain of this function is x is just not allowed to equal pi over 2 plus any integer multiple of pi. I usually say pi n, where n is an integer, but I won't write that out. You need to watch me do that. Okay, and then the range, this is kind of an interesting range here because it's kind of got 2 different pieces. Half the pieces, they go up above 1, so I could say y is greater than or equal to 1. But also we've got these lower pieces where y is less than or equal to negative 1. Okay. Now for the graph of cosecant, same idea. The window had a width of 2 pi because there was no horizontal dilation, which means that, okay, halfway to the edge of the window would be 1 pi, negative 1 pi over there. And so we see that it's 0, 1 pi, 2 pi, negative 2 pi. Okay, all of the vertical asymptotes are at integer multiples of pi, so these are the x values we need to exclude from the domain. X is not equal to pi times n, where n is an integer. And the range is going to be the same. Y is going to be either greater than or equal to negative, or greater than or equal to positive 1, or less than or equal to negative 1. So now if we want to graph y equals cotangent x, we're going to need to start with the idea of the graph of y equals tangent x. And so I'm just going to graph this. We've done this before. If you have no idea where this graph comes from, you could go back, and watch a video of me graphing y equals tangent x for the first time with lots of detail. I would remind you that the vertical asymptotes, well, tangent x is equal to sine x over cosine x, and the cos of a vertical asymptote is division by 0. So these are places where cosine x equals 0, and that's going to be, on this graph, pi over 2 and negative pi over 2. Okay, but this graph repeats itself. I just drew, a little bit of it. Repeats itself at intervals of pi, so I could say all of the vertical asymptotes, well, I could express those as pi over 2 plus pi times n, where n is an integer. And then it'll ask us, what is happening with cotangent x at the x values that correspond to vertical asymptotes of tangent? Okay, so I'm talking about pi over 2, negative pi over 2, and other coterminal angles. Okay, I'm going to think about the unit circle and kind of label those spots. Because I don't want to really reason with infinity here. That's just not mathematically legitimate, and I don't think it's the way to go. So what I'm going to be saying is, let's just think about the unit circle. Go back there. I'm interested in finding cotangent of theta at each of these theta values. Okay, so I need to think about the coordinates because I'm at the extremes. So the coordinates of that top point are 0 and 1. And so if I want to find cotangent of theta, I'm going to be taking the horizontal displacement, the x, divided by the vertical displacement, the y, and that's going to be 0 divided by 1, and 0 divided by 1 is just 0. Okay. And then if I think about what happens at theta equals negative pi over 2, okay, think about the coordinates, cotangent of theta will be the x coordinate divided by the y coordinate, 0 over negative 1, and that's still 0. So what's happening at x values that correspond to the vertical asymptotes of tangent is cotangent's going to equal 0. Okay. And then, just like before, places where tangent x equals 0, those will correspond to vertical asymptotes on the graph of y equals cotangent x. So keeping with that thought, okay, on the graph of tangent, the zeros become vertical asymptotes for cotangent. Let's plot these here. And that's a 0 over here of tangent. That's not a very straight vertical asymptote. Maybe I could do a little better on these. Okay. And then the vertical asymptotes on the graph of y equals tangent x become zeros of cotangent x. So let's plot those there. And then I'm going to get rid of some stuff. Much like before, I'm going to be thinking about intervals on which tangent x is positive. Cotangent x will also be positive because 1 over a positive number is positive. So maybe I'll just start with this first arm and get rid of it. Okay, tangent was positive through there, and so I know that tangent's going to continue to be positive. If it's going from 0 to a vertical asymptote while being positive, well, it's just going to have to look about like that. And then if I think about over here where tangent x was negative, okay, whoops, lost all the graph. Cotangent's also going to be negative while approaching a vertical asymptote. And so we see that it's kind of the same style of arms as the graph of y equals tangent x. They're just moving downhill. So I'm going to get rid of this and draw another one. And this one else. Okay, it's going to have to go through that. Okay, not a great sketch of the graph, but I think you get the point. It's the same arms as tangent. It just looks kind of upside down and shifted, and that really is what the graph of cotangent is with respect to tangent. All right, so where are the vertical asymptotes? Okay, on that front, well, I'm saying it's the x equals 0. I think out here this was x equals pi. So for the 0, yeah, that's going to be x equals pi because that's a 0 of tangent. The first 0 of tangent after theta equals 0. And then negative pi over there. Okay, yeah, and we know that tangent repeats itself on intervals of pi, so it's no surprise that cotangent does as well. And so if I was going to write an expression for these vertical asymptotes, it would be negative pi, 0, pi, probably 2 pi, 3 pi. This is going to be pi times n, where n is an integer. Okay, now, maybe you noticed that I just got the same vertical asymptotes that I got when I graphed y equals cosecant x. And it's like, okay, that's kind of interesting. Why would that be the case? And I might remind you, kind of two of our fundamental identities, that cotangent of theta equals cosine theta over sine theta, and cosecant theta is equal to 1 over sine theta. And thinking about where vertical asymptotes come from, well, there's zeros of the denominator. And because these functions have the same denominator, it's no surprise that they have the same vertical asymptotes. That's really all the new information I've got for you. Now I'm going to work some extra examples that, might be similar to some problems you might be confronted with sometime in the near future. So, we're going to start by finding the domain of f of x is cosecant of 1/3 of x plus pi over 2. What I'm going to do is I'm going to suggest we consider sine of 1/3 of x plus pi over 2. This is a reciprocal function. Because anytime this is 0, that will cause f of x to be undefined and having a vertical asymptote. So those will be the vertical asymptotes of f. Okay, and those will be the x values we'll remove from the domain, and that's how we'll find it. Okay, so I'm going to sketch the graph of just, a normal sine curve. Okay. And then I'm going to be thinking about the zeros of this function. So that would be 1, 2, 3. And hopefully that'll be enough for us to develop a pattern and, kind of like write a general expression for the vertical asymptotes for f. Okay, I really need to think about the horizontal aspects of this graph. So that's going to be the phase shift in the period. Okay, first I might think phase shift, that's the number that we've subtracted on the inside next to x. That would be negative pi over 2. Okay, and so that means that my window starts right there at x equals negative pi over 2. Then I think about the period. And the period is going to be 2 pi divided by b, where b is that like 1/3 number out on the outside, and 2 pi divided by 1/3, that's multiplying by 3, that'll be 6 pi. Alright, that tells me that the right edge of this window is negative pi over 2 plus 6 pi, so it'd be like 5.5 pi, that's 11 pi over 2. Okay, and then if I want to find that x value that's in the center, halfway between negative pi over 2 and 11 pi over 2, I'd just average them. I'd add the two values together and divide by 2. So if I added them together, I'd have 10 pi over 2. And if I divide that in half, I'd have 5 pi over 2. Okay, so I've got negative pi over 2, 5 pi over 2, and 11 pi over 2. And so I could think about, what's the distance between these values? Or I could think it's half the period, and that'd be 3 pi. Either way, no matter what, you're going to be thinking about adding 6 pi over 2 or dividing 6 pi by 2. Either way, you're going to find that the distance between these future vertical asymptotes of f would be 3 pi. So I'm going to just say that my vertical asymptotes of f are going to be, negative pi over 2 plus 3 pi n, where n is an integer. And as a result, the domain of f will be all x that isn't equal to negative pi over 2 plus 3 pi n, where n is an integer. Right, if we're asked to find the range of a function, I think we should sketch the graph of the reciprocal and let that kind of guide us. So when thinking about g of t, I'm going to really be considering for cosine of 2 pi times t minus 3 minus 5. Okay, and that's what I would sketch the graph of if I wanted to start sketching the graph of g. Okay, so I'll just sketch a old-fashioned cosine curve, and then I'll be thinking, okay, range, that's output values. I need to be thinking about kind of the vertical aspects of this function. So that would be like the midline, okay, and that's the number that's added onto the outside. That would be y equals negative 5. And I'll label my graph accordingly, but also the amplitude. And the amplitude is the vertical dilation factor. That would be a factor of 4, so the amplitude would be 4. That means I can go up by 4 and down by 4, so that means up to negative 1 and down to negative 9. Okay, and if you remember how the graph of secant and cosecant went, we can kind of just turn this thing inside out, draw some vertical asymptotes, we get some u's, we just the graph is outside of the box rather than inside the box. And so that just means that y is going to either be greater than or equal to negative 1 or less than or equal to negative 9 for g. And, if you're interested in producing the graph, that's what it would look like, but that's really not the point of this problem. If it's asking for the range, we don't need to draw the graph of g necessarily. We can just think about related functions and think what's going to happen. The next this is an interesting problem. So it says, let f of x equal 3 cosecant x. Let g of x equal 1 over f of x. Give a sketch of the graph of g. Okay, so I might just start working on g algebraically first. Okay, so I might say g of x is 1 over f of x, which is 1 over 3 cosecant x. But wait a second, 1 over cosecant, that would be the same as just like regular sine. So I'd have a 1/3 of sine x. Okay, but that's only true when f is defined. Okay, This is one of those situations where g is not always going to be defined, okay? Even though 1/3 sine x is. And I think the best, commentary I could give you on that, the best way to convince you, is that if f of x is undefined, how are you going to take 1 over undefined? That doesn't make any sense, right? That's not going to work. So g of x is not going to be able to be defined anywhere f of x is undefined. And we do know that f of x is undefined at places. It's got vertical asymptotes. So what I'm going to do is I'm going to just sketch the graph of y equals 1/3 sine x, and then maybe make a couple of adjustments. I'm going to take these places where sine x equals 0, which correspond to vertical asymptotes of f, and I'm just going to remove them from the graph. These are going to be, I don't know if we've used this terminology in this course, but what we would call a removable discontinuity, a hole in the graph. And, I think I'm just going to leave it at that. This is, mathematically speaking, a little intensive for AP Pre-Cal, a little bit on the fringe, but this is something I want you to be aware of. Now, the last example I've got for you, this is just one of those where we're just going to sketch the graph, right? Kind of what we built up towards the whole time. And I'm going to start by thinking about y equals 3 cosine of 2 pi over 5x. And then I'm just going to sketch that real fast because I think that's the part you're already good at. And then another thing I think you're probably already good at is knowing that this thing runs from -3 to 3 and with 0 in the middle. Okay, now what I'm going to do is I'm going to remind you, okay, well, there's no phase shift, so that means that the y-axis is going to continue to be right there at the left edge of my window. It's x equals 0. I already pointed out, actually, maybe I'll save the x-axis for last. I typically do that. I need to think about the period. Okay, so period is 2 pi over b, so that's 2 pi over 2 pi over 5. That's just going to equal 5. Okay, so 0 to 5, that'll make this 2.5, and that half one in the middle, 1 1/4, that's not 1.5, it's 1.25, and this would be 375. Okay, and now the zeros of cosine will correspond to the vertical asymptotes on the graph of secant. So I'm going to start by putting in those vertical asymptotes. And then I'm going to say, I think maybe it's time to get rid of the cosine curve. And the extremes will be shared points. I'll just kind of go up like this, down like that, and then another piece of graph over here. And there I've got a sketch of that function. Okay, so I think that's going to be all for this video. Thanks for watching.